All right, picking up with today the Unit 4 notes. We're finishing a projectile motion, and then we'll be covering the rest of it. Notice that we have for two-dimensional motion now, we're in two-dimensional motion, that the type of motion in the horizontal direction, for each one of these, we have a horizontal, and maybe I should do this in different colors, a horizontal component and a vertical component. All right, or in this case, it would be up on this side. All right, so for each one of those, we have that. And what you're going to find out is this guy would be 40. Let's do this in the right color. This would be 40. And this would also be 40. 40, if you remember the simulation we did, 40, 40, 40, and 40. And this would all be, of course, meters per second. Now, what you're noticing, or should be noticing, is as we go in green, is this starts at 30 meters per second, but since gravity is working against it, it's now slowing 10 meters per second. So at 2 seconds, it's 20, and then it's 10 meters per second. Then, of course, it's 0 meters per second. And then negative 10, negative 20, and then finally ends up at negative 30 meters per second. So what we see clearly is horizontally, we have constant velocity, and vertically, we have constant acceleration. Now, remember here also that we have horizontally, we have acceleration is equal to 0 in the x direction, but it's not equal to 0. It's equal to gravity in the vertical direction. Now the position equation is x final. Now for all of these, we're going to have x final equals x initial plus v initial t plus 1/2 at squared here, okay? We will also have v final equals v initial plus at. Now, what you should notice is that for constant velocity, that means that what we're going to end up having here is, and a 0 acceleration is for, in the x direction, this goes away. So we have x final equaling x initial plus v initial t, which is in the x direction. All right, velocity equation, velocity is going to be the same because that's going to go away. It's just going to be equal to v initial in the x direction the whole time. And then the initial velocity, v initial in the x direction, is of course going to be the x component, which would be v initial cosine theta. And of course, this v initial is the launch speed. Okay, so now for constant acceleration, we're going to get y equals y naught plus v initial in the y direction t minus 1/2 g t squared, because a is negative g in this case. All right, we're going to have v sub y, this of course should be v sub x, v sub y is going to be equal to v initial y minus gt, and then of course v initial in the y direction is going to be the initial velocity times the sine of the angle. All right, so now, if we want to figure something out here, what we know is that if we could find this final distance in the x direction, in other words, d is going to be equal to the initial velocity in the x direction, which would be 40 the entire way, meters per second. And it does this for 1, 2, 3, 4, 5, 6 seconds. So for 6 seconds, we end up going 240 meters that direction, okay? All right, so now let's look at a couple of examples. If we have a horizontal launch here, throw horizontally off the Chase Bank building. So we've got a bank building. We're going to throw something horizontally with an initial velocity v. We know that the bank building is 125 meters tall, and we know that this thing is going to go this way and land somewhere, boom, here. And it says 100 meters, so this is 100 meters away. All right, and it said, how fast did the student throw the ball? Well, what do we know? Well, what are we given? So we are given that the acceleration in the x direction is 0. The acceleration, and I'm going to do this in 2. Acceleration in the y direction is negative g, or negative 10. Okay. We are given that v initial in the x direction, we don't know, but we do know v initial in the y direction is 0 because they didn't throw it that way. They threw it sideways, horizontally. Now we also know that the distance, the initial, if we call this, and if we do a coordinate plane and we call this 0, 0, then we know x initial is 0 and y initial is 0. X final is 100 and y final is negative, or I'm sorry, yeah, negative. I'm sorry, I am incorrect. This is 125 meters is y, and x final is at 0 meters, okay? This is 100 meters to there. Okay, so how do we find this? Well, the first thing we're going to do is we're also going to find v. We don't know, but what we can find is v initial x and v initial y. And then we can put them back together again. Or really, v initial is just in the x direction. So how do we find this? We need to find time, don't we? So let's figure out what we know. And let's use the y to find the time. So we are going to find S and S, which is set up and solve. So we know y final is equal to y initial plus v initial in the y direction t minus 1/2 gt squared. Okay, well v initial in the y is 0, so that goes away. Y initial is 125, so we end up with 0 here. We have 125 here, minus 1. Well, guess what? We know this. We know x final is 100. X initial was 0. So this is v initial in the x direction times the time, which is 5. So v initial in the x direction was 20 meters per second. And so we know that since it's all in the x direction, then we know that v initial is equal to v initial x, which is 20 meters per second. So that's my answer right there. Okay? Sketch a graph of the following as a function of time. Okay. The horizontal distance started where? Now remember, for horizontal distance, we know this is a constant velocity. We found it was 20. So its constant velocity was 20 going this way, okay? For 5 seconds, and it stops here. Starts here and stops there. Well, we know what that means. We means that if it is a constant velocity of 0 acceleration, so this is going to be 0 in the horizontal, right to there. All right? Then we also know that the horizontal distance that it went starts at 0 and ends up going at 100. So this goes this way because we know its slope has to be equal to positive 20 meters per second, doesn't it? Which is our initial velocity in the x direction. Now, let's talk about vertical height. Vertical height. This thing started at 125 and it ended up at 0 down here at 5 seconds. But we do know that this had a velocity, but we also know it has an acceleration. It has a constant what? It has a constant acceleration. That constant acceleration is negative 10 for that entire time, okay? Because that's gravity. All right, well, then that means that the slope of this guy, the vertical velocity, well, the vertical velocity started at 0. And then we know after the first second, it was at -10. After the second -20. Third second, -30. The next second, -40. And the next one would then be at -50. And this would give me a slope of -10, wouldn't it? All right, well, if that's a diagonal negative, we know that the vertical height has to be starting at 0 and then changing until it gets to -5, which means it would be negative acceleration, which means it would be a concave down, so it's going to be doing this. So we can draw that in, okay? Now, things to remember about a horizontal launch is its horizontal initial velocity is equal to its launch speed. In other words, that V initial is equal to V initial x, right? Vertical initial velocity is equal to 0. In other words, V naught sub y is equal to 0. Projectile motion equations simplify to x final equals V initial times t, and y initial is equal to 1/2 gt squared. Good things to know, not on your formula sheet, but you can always get them. But these are good things to just memorize. Now, let's look at example 2. Tanner stands on the 30-meter line of a metric football field. Okay, so we've got a football field. And he's standing here. And he kicks a football at an angle of 53 degrees with an initial velocity, and it's going to land somewhere downfield. We know it took, well, we don't know how long it took, but what we do know is this is 53 degrees. We know its initial velocity is 25 meters per second. So we know initially that this V naught is equal to 25 meters per second. All right, so what we're going to have to do is we're going to have to find the initial in the x, and we're going to have to find V initial in the y for this guy. We don't know that for either one of them. All right, so we want to find the time the football is in the air. I'm going to give you a hint here, and typically, time the football is in the air is important. The easiest way to find that is to use the y direction in these types of problems, because we know the initial position is at 0, 0, and the final position is at x, 0. So y initial is equal to 0, and y final is also equal to 0, where the football comes back down. All right, so that's not such a big deal. We also know that V initial in the y direction is going to be V initial sine theta. So let's find it. That's going to be 25 sine of 53 degrees, which is equal to 20 meters per second. And you know what we also know? We know V final in the y direction, it's going to be the same speed going, but in the opposite direction. So it is negative 20 meters per second. This is going to help us and be even more handy. You can use either one of these to figure it out. Now I'm going to use this one first, and I'm going to say that y final is equal to y initial plus V initial in the y direction t minus 1/2 gt squared. So this is 0, and this is 0, and this is 20t minus 1/2 of 10 t squared. So we get half of 10 is 5t squared. If we move it to the other side, it's equal to 20t. So we get 5t equals 220, so t equals 4 seconds. So the time the football is in the air is 4 seconds. Now, to find the x distance, sometimes the easiest thing to do is to figure out how long. So now we're going to go to it, and we're going to say that x final is equal to x initial plus v initial in the x direction times t. Well, v initial in the x direction is going to be equal to v, which is 25, times the cosine of 53 degrees, which is equal to 15, excuse me, 15 meters per second. All right, so let's figure this out. We don't know where it ends, but we do know it starts at 0, because we called it 0, 0, plus 15 times 4. So it ends up at the 60, it ends up 60 meters. That would be delta x. But remember, it started at the 30-meter line, so we have to add 30 to that. It ends up at the 90-meter line. So really, we could have put that there, couldn't we? Okay. So anyway, highest height the football reaches. Well, the cool thing about that would be like right here. And what do we know? So right here, we know v in the y direction is equal to 0 right there. We also know the time here because it's symmetric. And if this is at 4 seconds, and this is at 0 seconds, then this is at 2 seconds. So at a time, t equals 2 seconds, v in the y direction is equal to 0. And we can figure out the height of this guy. Okay, we don't even end up needing that really, because what we know is y equals y initial plus v initial y t minus 1/2 gt squared. Well, y initial 0. We know v initial in the y direction was 20, so this is 20 times 2 minus 1/2 10 times 2 squared. So this is 40 minus half of 10 is 5 times 4 is 20. So it ends up being 20 meters is the highest the football reaches. Boom. Now, let's sketch a graph of this. We know it went for 4 seconds. The horizontal distance started at the 30-yard line, ended at the 90-yard line, and we know it was going a constant velocity. Its constant velocity was 15 the whole time for those 4 seconds. So this is going to be a diagonal straight line whose slope is 15. Okay. Now, we also know the acceleration is 0 here for 4 seconds because it has no acceleration in the x direction. Remember, this is constant velocity, and in the vertical direction, it is constant acceleration. Constant acceleration we know is -10 for 4 seconds. It started at +20, and we know it's going to end up at -20. So it's going to cross and be at its highest at 2. It's going to be at 0 velocity, because we found that from our picture. And this thing is going to, for that entire time, it's going to start at 0, and it's going to end at 0, and the highest it went at 2 seconds was 20. So here, we also know it has to be curved to look like a parabola. So boom, there we are. Ground-to-ground launch. Opposite velocities in the final vertical velocity is v in the y direction is equal to -v initial in the y direction, because it's going to be the same speed but opposite direction. And to use the time, we can use the time by plugging in v initial y and vy, which are same but opposite, into Vy equals V initial y minus gt. Also good to know to solve these types of problems. All right. Example 3, shooting at a wall. Here we go. If we're shooting at a wall, example 3, November 22nd, 1963, in an alternate universe, President Kennedy traveling down Main Street, book depository, shoom. Kennedy immediately draws a crossbow when Oswald shoots at him and shoots back at Oswald. All right. So he tries jumping out the window at the exact same time. What are the components of the arrow's initial velocity? Well, V initial in the x direction is going to be, what, 65 miles an hour? Okay, well, we have meters per second, 65 meters per second. We don't know what the angle is though, do we? Can we find the angle? We need to find the angle right here. Okay. We can do that. The angle theta right there, if we look at this, angle theta is going to be, if we do this, we can do sine or cosine. We could say the sine of that angle is equal to what? Or even better yet, because we know V initial in the x direction is V initial times the sine of theta. And we'll just use fractions for this. So sine of theta is going to be 100 opposite over hypotenuse, which is 260 here. Remember, this is opposite, this is adjacent, and this is hypotenuse. So we're going to say V initial was 65 times the sine, which would be 100 over 260. That is going to be 60 meters per second. V initial in the y direction is going to be V initial times the cosine of theta, which if we look is adjacent over hypotenuse. So this would be 65 times 240 over 260. And that ends up equaling 25 meters per second. So there we go for that. Height of the launch point, does the arrow reach the building? Okay, well, we know that y initial is 0. We are looking for y final. We know the acceleration is -10, and we do know the time. No, we don't. So maybe we should come back to this one and do what time does the arrow reach the building first? So for that one, we're going to say x equals what? X initial plus V initial in the x direction, t. Well, that's 0. We know this is 100, isn't it? No, 240. We're in the correct direction horizontally. 240 is equal to V initial in the x direction, which is 60 times t. So t is 4 seconds. Cool. So now I'm going to take that 4 seconds and bring it up here and say my time is 4 seconds. So now I can do y final is equal to y initial plus V initial in the y direction times time minus 1/2 gt squared. Okay. Y initial is 0. V initial is 25 times time is 4 minus half of 10 times 4 squared. So this ends up being 100 minus 80, which is 20 meters. So that's the launch point. Does it reach the building? At what height above the launch point is Oswald when the arrow reaches the building? Well, he is jumping from where? He's starting his y initial. This time is equal to 100. And we're looking for his y. We don't know. We know it would be after 4 seconds because that's when it hit. So he has 4 seconds to drop. And we know acceleration is -10 here. So we're going to figure this out. Y equals 100. What's his V initial, guys? If he's jumping, V initial, he's just dropping out. It's 0 in the y direction. So v initial in the y direction t goes away, minus 1/2 of 10 times 4 squared. So we're left with 100 minus 80, which is 20 meters. Uh-oh. So what happens? If this thing is at 20 meters above the launch point, but he falls from 100 down to 20 meters, then guess what? It looks like this. The arrow that he launches is going to go woo and then hit somewhere down here. But Oswald is going to go woo and fall down at the same spot at the same time. So guess what? Arrow hits Oswald Kennedy. How wily is that? So now let's start this. What is our horizontal velocity? Arrow's horizontal velocity is 60 and stays 60 the entire 4 seconds, doesn't it? The arrow's vertical velocity starts at what, 25? And ends at what? Well, it goes down by 10 every second. So from 25 to 15, from 15 to 5, from 5 to -5, and from -5 to -15. So this is his, because remember, gravity says it goes down by 10 meters per second per second. So we took it down by 10 each time. Oswald's vertical velocity starts at 0 and goes down by what? 10 each second. So 10, 20, 30, -40. So Oswald's vertical velocity is this. Okay. So now, last example here, example 4. Point O on the roof. We have a ball is shot from initial height of 8 meters with an initial speed of 10 meters per second, an angle of 37 degrees. Balls pass through point A. Okay, so what do we know? Immediately, I'm going to start with this. I'm going to say the horizontal velocity is going to be the same all the way through, which I need to find. This is going to be v initial times the cosine of, what, 37 degrees? So this is going to be 10 cosine 37. And this is going to be 10 sine 37, at least initially. So this, guys, is 8. And this is 6. So it starts at 8, but we know horizontal velocity is constant, so it stays at 8. This is at 6. And at the time, when is it going to hit the ground at point C? Ah. So we're going to have to find some stuff out here, aren't we? So let's figure this out. Time t is at 0 here. All right, so let's figure out what we've got here. We know that x is equal to v initial in the x direction times t. 6 projectile motion graph set to scale. Numerous scale represents the motion of the ball. Okay, so we got to figure out when it hits its maximum height. When is it going to hit its maximum height? Well, let's figure this out. Y naught plus v initial in the y direction t minus 1/2 gt squared. There's that guy. And we know this guy is going to be Vy is equal to V initial in the y direction minus GT. All right, so to find time A. We know that it starts at 0 or from 6 to 0. That's really what I want. I want to know time A, why do I go to 0? Because the vertical velocity at A is 0, because it's at the peak, isn't it? So the velocity in the y direction is 0 at this point. Okay, so we're using this equation, v sub y, v naught minus gt, so 6 minus 10 times t. So this is, t is going to end up equaling 0.6 seconds. Oh, that's perfect. So 0.6 seconds, which means then if it's going to go, so if this is 0, this is 0.6 seconds, then this has to be 1.2 seconds. We don't know what this is, so we're going to figure out, because it's not going to be the same. All right. To find time B, we're just going to double A. We're going to take 0.6 and multiply it by 2, which is 1.2 seconds. And to find time C, we're going to use the quadratic formula on this one, guys. Time at C, we need 2. All right, so how do we find time at C? What do we know? We know it started at what? Height of 8 meters. So its vertical height was at 8. Its horizontal distance is 0. So this is the point 0.8. But we know this is the point, what? Something 0. So its vertical height is 0 here. That's what we're going to use to find C. So we're going to say it ends up at 0, starts at 8, minus or plus v initial, which is 6 times t, minus 1/2 gt squared. All right, so I'm just going to move this half of gt squared, half of 10 is 5. Move it to the other side. I'm going to end up with 5t squared minus 6t minus 8 equals 0. And if I throw that in my calculator, I'm going to get t's. I'm going to end up with a t of approximately 2 seconds. And you can use the quadratic formula for this. All right, which would be negative b plus or minus the square root of b squared, which would be 36, minus 4a times c. 4 times 5 is 20, times c is plus 160, all divided by 10. Okay, and you'll get 2 out of that, or pretty close to it. All right, so this is 2 seconds, this is 1.2, and this is 2. So, what do we end up with here? We know this is 8, because that is at the same vertical height, so we need to figure out what the maximum height is. So let's do a little graphing and see if we can figure this out. Vertical velocity goes, it's the same here, so if it is 6, if it's 6 here, it's going to be exact and opposite here at negative 6. And then we do, let's use this formulas. Actually, I'm going to use the graphs. What do I know? It starts at position what? Well, 0.6, it's the same velocity the entire time. So this horizontal distance is going to be 0.6 times what? 8? The horizontal velocity is the same, right? The whole way through. So this is 4.8. This is going to be 1.2 times 8, which is going to be 9.6. And this is going to be 2 times 8, which is 16. And if you're wondering where this comes from, I'm using this formula right here. All right. So now I'm going to use the next formula I'm going to use is I'm going to use this formula for right here. Okay. So that's going to be what? Y initial well, Y initial was at 8. Y final we don't know. V initial we know all of this now, don't we? So I'm going to come over here in red and I'm going to do this one in red, and I'm going to say we want to know where it ends up. It started at 8, plus v initial was what? Vertical velocity was 6, times the time here is 0.6 seconds, minus 1/2 gt squared, so that'd be minus 5 times 0.6 squared. I took half of 10, guys, and got 5. And we are going to end up with approximately 9.8 meters. So this is going to be 9.8 meters. All right, last thing we need to know is the final vertical velocity. Well, the final vertical velocity here is after 2 seconds. So we know it's going to start with initial vertical velocity of 6 minus 10 times 2. So this is 6 minus 20, so negative 14. So this is negative 14 meters per second. All right, so now we know everything. Let's do all of these. So our x position, horizontal distance starts at 0. I'm going to do that in blue. If we start at 0 here, we take this to 10 and make this 20. And we're going to do 0.2, 0.4, 0.6, 0.8, 1.2, 0.4, 1.6, 1.8, and 2 seconds. So this is 2 seconds, 1.2 seconds, 0.6 seconds. Handy that, isn't it? All right. So at 0.6 seconds, it was at 4.8. So to 4.8 would be right about here. And then at 1.2 seconds, it's at 9.6, so right about here. And at 2 seconds, it is at 16, 12, 14, 16. So it goes in a straight line this way. Okay. Velocity then is going to be a straight line. That velocity, horizontal velocity is 8 the entire way. So I'm going to put 0 here, 2, 4, 6, 8, 10. I'm going to do 10 here. So my line would start here and go to here. All right. And this would be negative 10 down here. We're going to start at 0 here, 10 here, negative 10 here, and this is going to be 0 the whole way through. Okay, that's horizontal. So this is vertical. Vertically, we know it started at 8. I'm going to start at 0, 1, 2, 3, 4, 5, and 10's here. So it starts at 8, goes up to, and 0.2, 0.4, 0.6, 0.6 seconds, 0.8, 1, 1.2, and 2 seconds is here. So this is our time. So at 0.6 seconds, it was at 9.6. Then it was back to 8. And then it was down to, what? 0. And look, we can see that progression of it falling. Boom. We know it as a constant velocity, going down by 10 every second, but we're not going by seconds, are we? So if we're at 0 here, 0.6, 1.2, and 2. So 2, 1.2, 0.6. And the velocity starts at what? Vertical velocity started at 6, 2. And we got to go to negative 14, so this at 20 and go by 5, so this is 10, 5, 10, no, 4s. This is 8, 8, 12, 16, so here. So it started at, what, 6? Vertical velocity is at 6, so it's right here. This is 4, and we know it went to 0 here, and then it went to negative 6 here, and then ended up at negative 14. So 4, 8, 12, 16. This is 12, negative 16. So this would be halfway, right here. And look at that. That is a beautiful diagonal line showing that it has, if this is 0 and this is negative 10, a lovely constant acceleration. All right. Forces in equilibrium. sum of forces, if it's in equilibrium in the x direction, is equal to 0. Sum of forces in the y direction is equal to 0. Because equilibrium means that they balance. Left balances right. And up balances down. Forces. Okay? So, test your understanding. Each of the cases below shows the box of mass M suspended from 2 ropes. The grid on the background helps you see the different angles the rope can make. Okay, draw a free body diagram on the dot below each one. What do we know? Weight force is 4 vectors long. So we know down, 1, 2, 3, 4, 4 down, which means that we need to balance that. We need 2 up in each direction, don't we? So I need to go 2 up this way and 2 up this way with force of tension and force of tension. That also means that these guys, these components also matched, didn't they? Now we're not going to include those. So this would be, and then this would be what? Force of gravity down. Okay. So mg is again down by 4. Now this is a steeper angle. The first one was a steeper angle, so there was more up than there was down. Now this one's pretty much at a 45-degree angle, isn't it? This was kind of at 45, which means 45-degree angle, they split evenly, don't they? So we're going to go this way and this way. As long as it's still this 2 and this 2 up equals this 4, then we're okay. Now, last but not least, this is still 4 down, but look how steep this angle is. Most of the tension is going to be this way, isn't it now? So we still need to make that longer, but it would be like this and like this. So force of tension. I should label everything. Okay, but you can still see 2, 2, 4. And if you go the other way, 4 and 4. All right. All right, example. Spring scale. What do we know here? Act on the components. So let's draw a free body diagram first. So we've got here, so we've got mg downward. And we've got a couple of things happening here. We have force in the x direction here, this way, and force in the x direction this way. And we have force in the y direction happening twice here. So force in the y direction is going to be F cosine theta this time. Be careful with that because look where the angle is. Y is adjacent. And force in the x direction is going to be F sine theta this time. Okay? So be very careful about that. Now, I'm not worried about this one though, because really the only forces that I need to worry about are these right here that we can see balance each other out. Okay, so I know that twice the force in the y direction has to be equal to mg. Well, that is twice F cosine theta is equal to mg. All right, so we divide. Divide by 2 cosine theta. Divide by 2 cosine theta. That goes away. So we're left with F equals mg over 2 cosine theta. And that would be our answer. It's impossible for the angle to become 90 degrees and both ropes to become horizontal. Think about why that is. If it's 90 degrees, here's one reason. using your equation is the easiest, because what is cosine of 90 degrees? 0. And we can't divide by 0. So that would not work. And also, looking at all of these, if it were completely horizontal, in any one of these 3 cases right here, there would be we need a vertical force to balance with the force of gravity, F sub g there, don't we? So we need a vertical force, otherwise it's not in equilibrium, okay? So we need upward tension to balance with that downward gravitational force. All right, so let's do these guys. We know mg is this way. mg. Now, we have got the same horizontal tension, don't we? Do we? We don't have the same horizontal tension because the rope is angled differently every time. So we actually have very little. Most of this tension is in the vertical, which means it's not giving much horizontal. If we looked at horizontal, it'd be like 2 squares. So if we did think about it as 2 squares, we would have 2 squares this way of tension horizontal, and what? Oh, would it be 2 squares though? We could think of it as 2 squares. Sure. But if we do that, you know what I'm going to do? I'm going to think of this as in a different manner. What I want to do is think of this as in terms of the angle and what we just saw with that angle. It's mostly vertical. So I'm going to make it 1 square this way because this is very little horizontal and a whole lot of vertical, okay? So this is going to be my tension horizontal, and then I'm going to do like this to do my tension diagonal, okay? Now why did I do that? Because it gives me the 2 upward here to counteract this, and it gives me the 1 this way to counteract the 1 that way. Now this one's equal, so we're going to put this at a 45-degree angle that way, which means I have 2 this way and 2 this way. So 2 this way, 2 that way. I've already got my 2 up, down, so I need my 2 this way. So there's actually more horizontal tension than there was in the first case. Now, most of the tension is horizontal this way, isn't it? It's a really long horizontal and a little bitty this way, so it kind of should be a little bit of the reverse of the other. So we need it to be long and this way. So tension diagonal, we're going to have, to get the 2 this way, we're going to have 1, 2, 3, 4 that way. So we go 4 this way, tension horizontal. So on this one, I'll just go ahead and erase that part and just draw this back in. All right, spring scale. We know what? We know we have mg going this way, asking us to derive expressions, which means we're going to have to do math. We're going to use a free body diagram in this guy. I'm just drawing on the picture first because I know I'm going to have some force of A going this way, and I'm going to have force from B going this way. Okay? Those are both tensions, though, aren't they? So let's figure out what we got going here. Force of B, force of A is all in the horizontal direction. Force of B, however, is not. Force of B is going to have a component going this way in the x direction, which is going to be sine F sub B sine theta. Okay. And then we've got an x direction, or y direction. This will be kind of cool. Force to be in the y direction is going to be f sub b cosine theta. But you know what? We know what that is. Because we know that this guy and this guy, which is that, are equal because this thing is in equilibrium. So the first thing we know is in the y direction, we know that f sub b cosine theta is equal to mg. Okay. So f sub b is equal to mg over cosine theta. So that's f sub b. Now in the x direction, what do we know? Well, I know in the x direction I have f sub a and I have this guy. So what I know about that is I know that f sub a is equal to f sub b sine theta. Well, what is f sub b? Mg over cosine theta times the sine of theta. Well, sine divided by cosine is what? It's tangent. So this is going to be mg tan theta. So we've solved this. We've derived it. Impossible for theta to become 90 degrees. F sub a and f sub b. Well, what is the cosine of theta and tan theta? Are both then defined at 90 degrees. And we can't have better yet, still need, rather than saying can't have, still need upward tension to balance out mg. Okay. So next example. Sphere is held at rest by a long cord and a short cord. Yep, we got a long cord and a short cord right there. So we have T sub A and T sub B. Ball's weight is 5. So 1, 2, 3, 4, 5. This is mg. Cool. We know there's a lot more vertical tension in B and a lot more horizontal tension in A. So we need everything to match up. So since there's a lot more vertical in B, and we've got 5 here, we're going to split it between 1 and 4. So let's do this. So this would be my tension B. Well, this goes 2 this way, so this way would have to go this way. You know why? Because I have 2 this way, 2 this way. Those balance. And then I have 4, 5 to balance my 5 that way. Okay? And I don't want any extra markings on my free body diagram.